Welcome, fellow travelers, to Sleepy Science Quest, the place where we let our minds wander through the wonders of the universe, while our bodies drift gently toward rest. And tonight, I want to invite you on the ultimate journey, a trip not to a different country or a different planet, but a journey back through the deep, silent river of time to the very beginning of everything, to the moment before the clock even started ticking. So settle in, pull up your blankets, and let your imagination float freely as we try to build a universe together. To start this story, we have to try to do something that is almost impossible for a human brain to do, which is to imagine something so incredibly tiny that it practically doesn't exist at all. So I want you to picture a single proton, which is a tiny part of an atom. But even that is too big, because protons are so small that if you took a simple little dot of ink, like a period at the end of a sentence, you could pack 500 billion protons inside of it, which is a number so huge we can't really understand it. But just know that protons are microscopic specks, way smaller than dust, way smaller than anything you have ever seen. Now, I want you to take that tiny, invisible proton in your mind and shrink it down, make it smaller and smaller until it is 1 billion times smaller than it was before, squeezing it until it is so compact that the original proton would look like a giant mountain next to it. And this creates a space so tiny that we don't really have words to describe it. Now comes the hard part. The part where we have to become cosmic builders, because inside that vanishingly small space, we are going to pack in some matter, but not just a handful of sand or a cup of water. No, we are going to gather up everything that exists, every star you have ever seen in the night sky, every planet spinning around every sun, every mountain, every ocean, every person, every rock, and every cloud, gathering every single scrap of material from the edge of creation and squeezing it all into that one impossibly tiny spot we just made. You have to squeeze it and crush it until it has no size left at all, compacting it until it loses its dimensions and becomes something science calls a singularity, a point of infinite density where everything is hiding, waiting for the signal to begin. Now, you might think that while we are doing this experiment, we are standing in a dark room watching this tiny dot floating in front of us, like a balloon hanging in the air. But this is where our intuition tricks us, because in this moment before the beginning, there is no room, and there is no air, and there is no darkness surrounding our dot, because space itself hasn't been created yet. This is the hardest thing to visualize. But you must understand that the singularity isn't sitting in a blank space. It is the only thing that exists. So there is no outside, there is no around, there is nowhere you could stand to look at it, and there is no emptiness for it to expand into, because the emptiness doesn't exist either. It is just this one point, holding everything that will ever be, existing in a state of absolute solitude. And we cannot even ask how long this tiny point has been sitting there, waiting to explode, because time doesn't exist yet either. So there is no past, there is no before, there is no ticking clock counting down the seconds. There is just the singularity, perhaps appearing out of nowhere like a sudden thought, or perhaps having been there forever in a state of quiet suspension. It is a concept that breaks our brains a little bit. The idea of nothing being truly nothing, not even a black empty void, just a state of non-existence, except for our one tiny, packed, pressurized point of possibility. This is where our story begins, not with a bang, but with a silent, heavy anticipation, holding all the energy and matter of the future trapped in a cage smaller than an atom. waiting for the exact right moment to release the most beautiful and terrifying event in history. So as you lie there in the safety of your bed, try to feel the weight of that moment, the tension of an entire universe held in a breath, waiting to exhale and create the world. And so, we are hovering there in the unimaginable silence, watching that single pressurized point that holds all the hope and matter of the future. And then, without any warning, without a fuse being lit or a countdown being heard, the moment arrives. It is the moment that science calls $TEQU, ALS $0, the very first tick of the universal clock. And suddenly, that tiny trapped dot can no longer contain its burden. In a pulse of blinding glory that is too fast for our human words to truly describe, the singularity releases everything it has been holding. It does not explode into the dark, because remember, there is no dark yet. Instead, it creates the space as it rushes outward. It is a rapid, magnificent unfolding, like a flower blooming at a speed faster than light, or a blanket being thrown out over a bed that stretches on forever. Where there was once absolutely nothing, not even emptiness, there is now suddenly a here and a there, a vast and growing canvas of space that pushes out in every direction at once. It is the most violent and beautiful event that will ever happen, a glorious birth that turns the impossible into the possible, transforming a point with no dimensions into a kingdom of heavenly size. In that very first second, a single second that is so packed with action that scientists will spend their entire lives trying to understand just tiny, thin slices of it, the universe comes alive. It is a lively, frantic second where the rules of the game are written. Before this moment, there was no up or down, no heavy or light. But now, in the midst of this chaotic expansion, the great forces that govern our lives decide to wake up. Gravity appears, reaching out with its invisible hands to start pulling things together, creating the anchor that will one day hold your feet to the ground and keep the Earth spinning around the sun. Along with gravity, the other forces of physics rush onto the stage, the forces that control electricity and magnets, and the tiny glue that holds atoms together. They all arrive in this first breath of creation, locking into place, setting the settings for how the universe will work for the rest of eternity. It is a time of wild transformation, where the universe is growing so fast that in less than 60 seconds less time than it takes you to fluff your pillow and get comfortable, this baby universe has stretched from being smaller than an atom to being 1,000,000 billion miles wide. It is expanding faster than we can think, racing outward to carve out a place for itself, growing from a speck of dust into a titan that dominates the void it is creating. As this expansion happens, you must imagine the heat. It is not just warm like a summer day, or hot like the inside of a volcano. It is a heat beyond comprehension, a searing temperature of 10 billion degrees. It is so hot that matter as we know it cannot truly exist yet. Nothing solid can survive this inferno. Instead, everything is a soup, a thick, swirling, energetic broth of particles crashing into each other, dancing and colliding in the glowing radiance of the birth of time. It is a nuclear furnace on a cosmic scale, a storm of energy that is cooking the ingredients of reality. And inside this fiery storm, the very first elements begin to form. The universe is acting like a great cosmic chef, mixing the raw energy together to create the simplest building blocks of matter. In this intense heat, the universe begins to manufacture the lighter elements. the simple gases that will become the grandparents of everything else. 1. It starts churning out hydrogen, the most basic element of all, and helium, its slightly heavier cousin. It manages to sprinkle in a tiny dash of lithium, just a pinch, about 1 atom for every 100 million others, like a chef adding a rare spice to a massive pot of soup. This is the great production line of the Big Bang, a factory working at a speed we can hardly fathom, turning pure energy into the gas that will eventually fill the stars. But it doesn't make everything. It doesn't make the carbon for your skin, or the iron for your blood, or the oxygen for your lungs. It is in too much of a rush for that heavy lifting. It focuses only on the simple stuff, the light gases, filling the expanding balloon of the universe with vast clouds of hydrogen and helium. And the most amazing thing about this entire dramatic performance, this sequence of gravity waking up, space stretching out 1 billion miles, and the great nuclear ovens cooking up the vast majority of all the matter that will ever exist, is how quickly it happens. You might think that building a universe would take an eternity, a slow and laboring process of brick-by-brick construction, but the universe is impatient. It does not wait. From the moment the singularity popped to the moment where 98% of all the matter in existence was created, only 3 minutes have passed. 3 minutes. That is it. Think about that for a moment as you lie there in the quiet. In the time it takes you to walk to the kitchen, take 2 slices of bread, spread some peanut butter and jelly on them, and put them on a plate. In the time it takes to make a simple sandwich, the universe did all the hard work. It went from being a dimensionless dot of nothingness to a massive, sprawling, cooling expanse filled with the gases that would one day become stars. It finished the heavy lifting of creation before you could even finish a song on the radio. After those first 3 frantic, fiery minutes, we have a universe. It is a place of wonder, a place of infinite possibility, stretching out in the dark, still glowing with the heat of its birth, but starting to settle down for the long, slow journey ahead. It is beautiful, it is vast, and it is ready for the next chapter, all created in a burst of energy so swift that if you had blinked, you might have missed the beginning of everything. We have arrived. We are on our way. The silence of the void has been broken, and the great story of us has officially begun. Now that we have built our universe and cooked up all the ingredients in the first few furious minutes of creation, a very natural question pops up in our minds. When exactly did all of this happen? If we were to look at a calendar of the cosmos, how far back do we have to flip the pages to find that first day? It turns out, this is a very difficult question to answer, and for a long time the scientists who study the stars, the cosmologists, argued quite a bit about it. Some said it was 10 billion years ago, others said it was 20 billion, and the debate went back and forth for years. But eventually, everyone started to agree on a number right in the middle. The best guess we have, the number that most scientists agree on today, is that the moment of creation, that magical time we call $TQU, ALS $0, happened about 13.7 billion years ago. That is a number so big it is hard to really feel it. But just know that it was a very, very long time ago, in the deep, distant past, when suddenly, for reasons we still don't quite understand, we were on our way. But here is the strange thing about this story. Even though today we talk about the Big Bang as if it is a normal fact, like the Earth being round or the sky being blue, it is actually a very new idea, For a long time, people didn't really think the universe had a beginning like that. The idea first appeared in the 1920s, suggested by a Belgian priest and scholar named Georges Lemaitre, but it was just a theory, a quiet guess that didn't get much attention. It wasn't until the mid-1960s, which, in the grand scheme of things, is practically yesterday, that the Big Bang became real to us. And the most wonderful part of this story is that the proof for the birth of the universe wasn't found by a genius sitting at a chalkboard writing down complex equations. It was found by accident. It was found by two young astronomers who were actually looking for something else entirely, and who were mostly just annoyed by a noise they couldn't get rid of. Their names were Arno Penzias and Robert Wilson. In 1965, these two young men were in Holmdel, New Jersey, trying to use a very large, very sensitive antenna. This wasn't just a normal radio antenna. It was a giant piece of equipment owned by Bell Laboratories, and they wanted to use it to listen to the quiet signals from the galaxy. They wanted silence so they could hear the whispers of the stars. But there was a problem. No matter what they did, they could not get silence. Every time they turned on their machine, they heard a noise. It was a background noise, a steady, steamy hiss that just wouldn't go away. It wasn't a signal with a message. It was just static, unfocused, and unrelenting. It drove them crazy. It made doing their actual work impossible because the hiss drowned everything else out. So, like anyone trying to fix a broken radio, they tried to figure out where it was coming from. They pointed the antenna at the city of New York, thinking maybe the noise was coming from the hustle and bustle of the people there, but the hiss remained. They tested it during the day and they tested it at night, thinking maybe the sun was causing interference, but the hiss was still there. They checked it in every season, through summer and winter, and it never changed. The noise came from every single spot in the sky, no matter where they pointed their dish. It was everywhere. For a whole year, these two patient astronomers tried to fix this broken machine. They acted like detectives. They checked every single electrical system. They rebuilt the instruments. They wiggled the wires and dusted off the plugs, hoping to find a loose connection. They even climbed right inside the giant dish with duct tape, taping over every seam and every rivet, trying to smooth out the surface. They grew so desperate that they started blaming the local wildlife. A pair of pigeons had been roosting in the antenna, and as birds do, they had left a mess behind. In their scientific papers later, the astronomers politely called this mess white dielectric material, but you and I know it more commonly as bird poop. So, Penzias and Wilson climbed into the dish with brooms and scrubbing brushes, cleaning away the white dielectric material and shooing away the birds, convinced that this was the cause of their headache. But nothing worked. They scrubbed, they taped, they rewired, and still the hiss remained. It was a steady, mysterious static coming from all directions of the universe. Now, here is where the story takes an ironic twist. While Penzias and Wilson were scrubbing bird droppings in New Jersey, completely baffled by this noise, there was a team of very smart scientists just 30 miles away at Princeton University. This team, led by a man named Robert Dick, was actually looking for the very thing that Penzias and Wilson were trying to throw away. The Princeton team was working on an idea from the 1940s by a Russian scientist named George Gamow. Gamow had predicted that if the Big Bang had really happened, the massive explosion would have left behind a ghost, a faint glow of radiation that would still be traveling through space billions of years later. He said this radiation would have cooled down over time and turned into microwaves. He even suggested that if you had the right instrument, like the Bell antenna at Holmdel, you could probably hear it. But Penzias and Wilson hadn't read that paper. They didn't know that the annoying static was actually the most important discovery in history. Eventually, running out of ideas, they called Robert Dick at Princeton to ask for advice on how to fix their noisy machine. As Dick listened to them describe the problem, a hiss coming from everywhere day and night that couldn't be fixed, he realized immediately what had happened. He hung up the phone, looked at his colleagues and said, "Well, boys, we've just been scooped." The two young men in New Jersey hadn't found a broken wire or bird mess. They had found the edge of the universe. The static they were hearing was the ancient light from the Big Bang itself. They were seeing the first photons, the oldest light in existence, which had traveled for billions of years, stretching out over time until it turned into a microwave hiss. To give you an idea of how amazing this is, imagine you are on the 100th floor of the Empire State Building. Before this moment, looking deep into the universe was like looking down to the 60th floor. We could see distant galaxies, but that was it. But with this discovery, suddenly, we could see all the way down to the sidewalk. We were looking at the very foundation of everything. Even though Penzias and Wilson weren't looking for this discovery, didn't know what it was when they found it, and didn't even understand it until they read about it in the newspaper later, they were the ones who found the proof. They were awarded the Nobel Prize in Physics in 1978. The Princeton researchers who knew what to look for but didn't find it got only sympathy. And the most amazing thing is that you can see this proof too. If you have an old television set, the kind with antennas, and you tune it to a channel that doesn't exist, you will see dancing black and white static. About 1% of that static is caused by this same ancient background radiation. So, the next time you complain that there is nothing good on TV, just remember, you are actually watching the birth of the universe, the flickering afterglow of the Big Bang, dancing right there on your screen. So we have found the proof. We have seen the static on the TV screen and heard the hiss in the antenna that tells us, without a doubt, that our universe began with a massive event billions of years ago. But now that we know that it happened, we have to face a much harder question. How did it happen? And perhaps more importantly, what exactly was it? When we hear the name Big Bang, we all tend to picture the same thing. We imagine a giant stick of dynamite exploding in the dark, blowing pieces of shrapnel and debris outward into an empty room. But this is where the universe tricks us again, because the Big Bang wasn't really an explosion at all. An explosion is something that happens inside a space, pushing things apart. But remember, there was no space. The Big Bang was an expansion. It was space itself, stretching out, rushing away in all directions. It wasn't like a bomb going off. It was more like a balloon suddenly inflating, or a loaf of bread rising in the oven, carrying all the raisins, the galaxies along with it. But what triggered it? Why did that tiny, peaceful singularity suddenly decide to wake up and grow? Scientists have many theories about this. Some think that maybe our universe is just one of many, like a bubble in a giant pot of boiling water. and we just happen to be inside one bubble that popped into existence. Others think that maybe the nothingness before the universe wasn't empty at all, but was filled with something called vacuum energy, a strange instability that just couldn't sit still. It seems impossible to get something from nothing, but the fact that we are here is proof that somehow you can. But the real hero of this part of the story is a specific idea that explains how we got from a tiny dot to a massive cosmos so quickly. This idea is called inflation theory, and it comes from a man named Alan Guth. In 1979, Alan Guth was a young physicist, just 32 years old. By his own admission, he hadn't done anything particularly world-changing yet. He was just a junior researcher working at Stanford. But one day he happened to go to a lecture on the Big Bang. And guess who was giving the lecture? It was Robert Dicke, the same scientist from Princeton who had missed out on the Nobel Prize for the antenna discovery. That lecture sparked a fire in Alan Guth's mind. He started thinking about the very first moments of creation, the tiny fraction of a second right after the clock started. Guth realized that for the universe to look the way it does today, so smooth, so huge, and so perfectly spread out, something wild must have happened right at the start. He proposed that a fraction of a moment after the dawn of creation, the universe didn't just expand, it inflated. It ran away with itself. Imagine a speck of dust suddenly doubling in size, then doubling again, and again, and again. Now imagine this happening so fast that it doubles every $10 circumflex, minus $34 seconds. That is a decimal point, followed by 33 zeros, and then a 1. It is a slice of time so thin, it doesn't even feel like time. In this mode of inflation, the universe went crazy. In less than the blink of an eye, in fact, in a sliver of time that makes a blink look like 1,000,000 years, the universe went from something you could hold in your hand to something vast, stretching out billions of light years across. This theory, this inflation, changed everything. It explained why the universe is so big. But it also explained something else very important: the texture of the universe. If the Big Bang had just been a smooth, steady expansion, the universe might have ended up being just a boring soup of gas, with no clumps, no clusters, and no stars. It would have been a dark, lonely fog, but inflation was violent and fast, and it created tiny ripples or eddies in the fabric of space. Think of it like a wave crashing on the shore. It leaves behind little ripples in the sand. Inflation left behind ripples of density, tiny little pockets, where there was slightly more stuff than in other places. These little pockets, these tiny imperfections caused by the chaotic speed of inflation, are the reason we exist. Because those little clumps of matter had slightly more gravity than the empty spaces around them, they started to pull more dust and gas toward them. Over millions of years, these clumps grew and grew until they ignited to become stars and galaxies. Without that frantic runaway growth spurt in the first fraction of a second, we would just be drifting gas in everlasting darkness. So, thanks to Alan Guth and his idea of inflation, we understand that our universe started with a sprint, a sudden blinding dash from tininess to greatness, setting the stage for all the stars and galaxies that light up our sky tonight. We went from a proton-sized speck to a canvas of infinite possibility, all in a heartbeat. Now that the Big Bang has banged, and the universe has inflated from a tiny speck to a massive, sprawling canvas of space, we have to pause and look at what we actually have. It is one thing to create a universe to make a lot of space and fill it with gas, but it is another thing entirely to make a universe that is interesting. You see, it would have been very easy for the Big Bang to produce a mess. It could have created a universe that was just a thick, dark soup where nothing ever happened, or a universe that collapsed back on itself instantly, like a failed soufflé. But that isn't what happened. Against all odds, we ended up with a universe that allowed for stars, galaxies, planets, and eventually people to sleep in warm beds and wonder about where they came from. This brings us to one of the most mysterious and beautiful parts of our science quest, the incredible precision of our creation. When scientists look at the forces that hold the universe together, they find something that makes them scratch their heads in wonder. It turns out that for you and me to exist, the universe had to be set up perfectly. And when I say perfectly, I don't mean pretty good. I mean exact, down to the tiniest decimal point. Let's talk about gravity for a moment. We all know gravity as the thing that makes things fall down, but in the early universe, gravity was the sculptor. It was the force that pulled clouds of gas together to make stars. If the Big Bang had given us a universe where gravity was just a tiny bit stronger, just a fraction of a fraction more powerful, the universe would have been a disaster. It would have collapsed like a badly erected tent. Everything would have crunched back down into a singularity before life ever had a chance to start. But what if gravity had been a little bit weaker? Well, that would have been just as bad. If gravity was too weak, the dust and gas would never have come together. They would have just floated away from each other, drifting forever in a dull, scattered void. There would be no stars, no heat, no light, just an endless cold, dark fog. But we didn't get the crushing universe, and we didn't get the drifting fog. We got the one in the middle. We got the gravity that was just right strong enough to build stars, but weak enough to let the universe keep expanding. It isn't just gravity either. There is a whole dashboard of settings in the universe that seem to be tuned exactly for us. Consider the nuclear forces inside an atom. For the universe to work, hydrogen has to turn into helium in a very specific way. It has to convert exactly 7 1,000ths of its mass into energy. That is 0.007%. It sounds like a boring number, but your life depends on it. If that value was slightly lower, say 0.006, the transformation wouldn't happen. The universe would be nothing but hydrogen. Forever. No helium, no heavier elements, no us. On the other hand, if the value was just a tiny bit higher, say 0.008%, the hydrogen would have burned up frantically and exhausted itself billions of years ago. In either case, with just the slightest tweak of the numbers, the universe as we know it, the universe we need, would not be here. It is like trying to balance a pencil on its sharpest point. If it leans even a microscopic amount to the left or the right, it falls. And yet, here we are, balancing perfectly on the point. This leads to a very big question. Why? Why did we get so lucky? Why are the laws of physics set up exactly the way they need to be for us to exist? Some scientists, like Edward P., Tryon suggests that maybe universes are just things that happen from time to time, and we shouldn't overthink it. It's a modest proposal, that perhaps we are just a random event. But others think there is a more expansive answer. Martin Rees, a very famous astronomer from Britain, believes the answer might lie in something called the multiverse. Imagine you are shopping for a suit or a dress in a truly gigantic clothing store. If there was only one suit in the store, and you tried it on and it fit you perfectly, arm length, waist size, everything exact, you would be amazed. You would think it was a miracle. But if the store is the size of a city, and it contains millions and millions of suits in every possible size and shape, then finding one that fits isn't a miracle at all. It is inevitable. You simply kept looking until you found the one that worked, and that is the one you are wearing. Rees thinks our universe is like that suit. Rees thinks our universe. He believes there might be infinite universes out there, bubbles and bubbles of creation floating in the span of eternity. In some of them, gravity is too strong, and they collapse. In others, the nuclear forces are too weak, and they stay dark forever. There might be trillions of failed universes, empty and dead, where the numbers didn't line up. But because there are so many of them, eventually, just by chance, one appeared where the numbers were perfect. One appeared where the clothing fit. And because this is the only kind of universe where life can survive, this is naturally the one we find ourselves in. We couldn't be in the others because we wouldn't exist to notice them. So, whether it is a multiverse or just an incredible stroke of luck, we can take comfort in the fact that we are the winners of the cosmic lottery. We are living in the Goldilocks universe. Not too hot, not too cold, not too fast, not too slow. Everything is just right. As you drift off to sleep tonight, you can feel safe knowing that the very forces of nature, the deep invisible numbers of creation, are balanced perfectly to hold you, the earth, and the stars in place. The universe might be wild and vast, but it is also quite literally made for us. Having marveled at how perfectly our universe is balanced, sitting there in the Goldilocks zone where everything is just right for life to exist, we now have to ask the mechanical question, how did it get that way? It is one thing to say the universe is perfect, but it is another thing to explain how a tiny, hot dot of energy transformed into a massive, smooth, star-filled cosmos so quickly. To understand this magic trick, we have to look at the very specific mechanics of the expansion itself. We have to look at a moment in time that was so fast it barely existed, yet it determined the shape of everything we see today. This brings us to the story of a man named Alan Guth and a concept that changed science forever. Inflation theory. Most of what we know, or believe we know, about those first fleeting moments comes from an idea that popped up in 1979. Alan Guth was a young physicist at the time, 32 years old, working at Stanford University. He was a modest man who, by his own admission, hadn't done anything particularly history-making in his career yet. He was just a junior researcher. But his life changed because he decided to attend a lecture on the Big Bang. And in a lovely connection to our earlier stories, the man giving that lecture was Robert Dick, the same scientist from Princeton who had been hunting for the cosmic background radiation, only to be scooped by the accidental discovery in New Jersey. That lecture sparked something in Guth's mind. It inspired him to look closer at the birth of the universe, specifically at what happened immediately after the clock hit zero. He began to run the math, and what he found was startling. He realized that the standard idea of a slow, steady expansion couldn't explain why the universe was so big and so uniform. There had to be something else, a mechanism that acted like a turbocharger right at the starting line. Guth proposed that a fraction of a moment after the dawn of creation, the universe underwent a sudden, dramatic and violent change. It didn't just expand, it inflated, it ran away with itself. To visualize this, we have to stretch our imaginations. Imagine a tiny speck, something infinitesimal. Guth's theory suggests that this speck started doubling in size. But it didn't just double once a year or once a day. It doubled every 10 to the minus 34 seconds. That is a decimal point, followed by 33 zeros. It is a slice of time so thin that it is effectively instantaneous to us. But in the quantum world, it was enough time for the universe to go wild. In this mode of inflation, the universe kept doubling and doubling and doubling, expanding at a speed that defies logic. The whole episode may have lasted no longer than a millionth of a millionth of a millionth of a millionth of a second, but that was enough. In that breath, the universe changed from something you could hold in the palm of your hand to something at least 10 sextillion 000 times bigger. It went from a subatomic particle to a vast cosmos in a heartbeat. This theory of inflation is crucial because it explains the texture of our world. You see, if the universe had expanded slowly and gently, it might have been too perfect. The gas and energy would have spread out completely evenly, like a perfectly flat sheet of ice. If that had happened, gravity would have been helpless. Gravity needs clumps to work. It needs a pile of dust here or a cloud of gas there to start pulling things together. In a perfectly smooth universe, there are no clumps, which means no stars, no galaxies, and no planets. Just a dark, drifting fog forever. But inflation was not gentle. It was a violent, chaotic stretching of space. And just like stretching a piece of rubber too fast, it left behind tiny imperfections. It created faint ripples and eddies in the fabric of space. These microscopic ripples created the first clumps of density. They were the seeds. Because of these tiny irregularities caused by the speed of inflation, gravity had something to latch onto. It pulled the dust into these ripples, building them up over billions of years, until they ignited into the galaxies we see today. So without that frantic runaway expansion, we would not be here. And then, just as quickly as it started, the inflation stopped. The runaway train hit the brakes. And this leads to the second miracle of this moment, the arrival of matter. According to the theory, before this moment, the universe was mostly pure energy and potential. But as the inflation ended, that energy had to go somewhere. In a single, cracking instant, the energy of the expansion converted into stuff. It is the ultimate magic trick of physics energy, turning into mass. Suddenly, from nothing at all, the void was filled with swarms of particles. We are talking about the birth of the building blocks of reality. Swarms of photons, protons, electrons, and neutrons flooded the new emptiness, and the numbers are staggering. Science tells us that between 10 to the 79th, and 10 to the 89th particles were created in that single pulse. Think about that number for a second as you drift towards sleep. A 1 followed by nearly 90 zeros. It is a quantity of matter that is ungraspable. It is enough to build every star in every galaxy, every planet, every ocean, every grain of sand, and every single cell in your body. All of it appeared in a single blinding moment of glory, a moment too swift for words, endowing us with a universe that was vast, heated, and perfectly arrayed for the creation of complex systems. So, we have a universe that is huge, thanks to inflation. We have a universe that has texture and stars, thanks to the ripples left behind by that inflation. And we have a universe filled with matter, thanks to the energy conversion that happened when the inflation stopped. It was all done in less than a second, setting the stage for the billions of years of history that would follow. We were no longer just a singularity, we were a cosmos, vast and ready for life. So, we have arrived at a moment where the universe is filled with stuff. Thanks to the wild ride of inflation and the sudden conversion of energy, we have a cosmos that is vast, stretching out for billions of light years, and teeming with swarms of protons, electrons, and neutrons. We have the canvas, and we have the paint. But as any artist knows, just having the materials doesn't mean you are going to end up with a masterpiece. You need a steady hand. And this brings us to the most mysterious and unsettling part of our story. The fact that our universe seems to have been built with a precision that is almost impossible to believe. What is truly extraordinary from our point of view isn't just that the universe was created, but how incredibly well it turned out for us. You see, building a universe is a bit like baking a very complicated cake. You can't just throw everything in the bowl and hope for the best. You need the temperature to be exact, the measurements to be precise, and the timing to be perfect. If you get any of those things wrong, even by a tiny bit, the cake collapses. In the case of our universe, the ingredients are the laws of physics, the invisible rules that tell matter how to behave. And the scary truth is, if those rules had been set even slightly differently, we wouldn't be here to talk about it. Let's look at gravity first. We usually think of gravity as just the thing that keeps our feet on the ground or makes an apple fall from a tree. But in the early universe, gravity was the great architect. It was the force responsible for grabbing those clouds of gas and dust and squeezing them together until they grew hot enough to ignite into stars. Without gravity, there are no stars, no heat, and no light. Now, imagine gravity is controlled by a dial, like the volume knob on a radio. If, at the moment of the Big Bang, that dial had been turned up just a tiny fraction higher, making gravity just a trifle stronger, the universe would have been doomed from the start. A stronger gravity would have pulled everything back together too quickly. The expansion of the universe would have stopped almost as soon as it began. Instead of stretching out into a beautiful, open cosmos, the universe would have collapsed, like a badly erected tent. All the matter would have rushed back inward, crushing itself down into a dense, fiery crunch before life ever had a chance to begin. It would have been a universe that lived and died in a heartbeat. But what if we turned the dial the other way? What if gravity had been just a tiny bit weaker? Well, that would have been just as disastrous, but in a different way. If gravity were weaker, it wouldn't have been strong enough to pull the gas clouds together. The force of the expansion would have overpowered the force of attraction. The dust and gas would have just kept drifting apart, floating further and further away from each other in the dark. Nothing would have coalesced. There would be no clumps, no stars, no galaxies. The universe would have remained forever a dull, scattered void, a cold, empty place where nothing ever happened. We exist on a knife edge between these two disasters. We live in a universe where gravity is strong enough to build stars, but weak enough to let the universe keep growing. It is balanced perfectly. But gravity isn't the only thing that had to be perfect. There are other numbers deeply hidden in the code of the universe that are just as critical. One of the most famous examples involves the way atoms work. For the universe to be interesting, it needs to be able to turn simple hydrogen into helium. This process creates the energy that powers the stars, including our own sun. It is a nuclear reaction, a cosmic fire. The way this works is governed by a very specific number. When hydrogen turns into helium, it converts exactly 7/1000ths of its mass into energy. That is 0.007%. It sounds like a boring throwaway statistic, the kind of number you would scroll past without thinking. But your life, and the life of every living thing, hangs on that number. Let's play the what-if game again. Imagine that value was slightly lower. Let's say it was 0.006% instead of 0.007%. That sounds like a tiny change, right? Just a rounding error. But if that number was 0.006%, the proton and the neutron wouldn't be able to bond together. The transformation from hydrogen to helium simply wouldn't happen. The nuclear fire would never light. The universe would be filled with nothing but cool, lonely hydrogen gas. There would be no chemistry, no complexity, and certainly no us. Now, let's go the other way. What if the number was slightly higher? Let's raise it to 0.008%. Again, a change so small you would need a microscope to see it. But if the value were 0.008%, the bonding would be too good. It would be wildly prolific. The hydrogen would have fused so easily and so fast that it would have all been used up in the first few moments of the Big Bang. All the fuel in the universe would have burned out billions of years ago, leaving nothing behind but dead ashes. There would be no hydrogen left today to fuel our sun or to form water. In either case, -0.006 or 0.008, the slight tweaking of the numbers results in a dead universe. It is only at exactly 0.007% that we get a universe that burns slowly, steadily, and sustains life for billions of years. Martin Rees, a very wise astronomer, points out that there are 6 of these numbers in particular that govern our universe. If any one of them were changed even very slightly, things could not be as they are. It is as if we are walking down a very narrow hallway. On one side is a wall of fire, on the other side is a wall of ice, and the path we have to walk is razor thin. Yet somehow we have managed to walk right down the middle without stumbling. Cosmologists, in their lighter moments, like to call this the Goldilocks effect. You remember the story of Goldilocks, who broke into the bear's house and tried their porridge. One bowl was too hot, one was too cold, but the third one was just right. That is exactly where we live. We live in the just right universe. Everything about our home seems to be custom-fitted for our existence. The dimensions are right, the density is right, the component parts are right. If the expansion had proceeded just a little more slowly or swiftly, if the nuclear forces were just a whisper different, we wouldn't be here. It is a thought that is both terrifying and comforting. It makes you realize how fragile we are, suspended in this vast dark space, only because the settings of the universal machine are tuned to perfection. We are the beneficiaries of a cosmic stroke of luck that is almost impossible to calculate. So, as we settle into this realization, looking at the perfect balance of forces that keeps our blood flowing and the earth spinning, a big question naturally starts to form in our minds. Is it really just luck? Did we just happen to win the biggest lottery ticket of all time? Or is there another explanation for why everything fits us so well? To answer that, we have to step out of our universe entirely and imagine something even bigger. But that is a story for the next part of our journey. So, we are left staring at this mystery of the just right universe. We are living in a place where gravity, nuclear forces, and the speed of expansion are balanced on a razor's edge, tuned so perfectly that if they were even slightly different, we wouldn't be here. It feels like a miracle. It feels like someone set up the board specifically for us to win the game. But science doesn't really like the answer, it's just magic. Science wants a reason. And this desire for a reason leads us to one of the most fascinating and mind-expanding ideas in all of cosmology. It suggests that perhaps our universe isn't the only universe. This brings us to the concept, the multiverse. To understand this, we have to change the way we think about luck. Imagine you buy a lottery ticket. The odds of winning are 1 in a billion. If you buy one single ticket and you win the jackpot, that is an incredible, unbelievable stroke of luck. You would be on the news. People would call it a miracle. But imagine if you bought every single ticket in the lottery. Imagine you bought 1 billion tickets, covering every possible combination of numbers. Now, if you win, is it luck? No. It is a certainty. You were guaranteed to win because you tried every possibility. Many scientists, including Martin Rees, who holds the fancy title of Britain's Astronomer Royal, believe that this is exactly what is happening with our universe. They suggest that our Big Bang wasn't a one-time event. They propose that Big Bangs are happening all the time, all over the place, in a vast, unending ocean of eternity. This is the theory of the multiverse. It suggests that our universe is just one bubble in a giant foam of bubbles. Martin Rees uses a wonderful analogy to explain this, one that is very easy for us to picture. He asks us to imagine a clothing store, but this isn't just a regular shop at the mall. This is a clothing store of infinite size. It has racks of clothes that stretch on forever. Now, imagine you walk into this store looking for a suit or a dress. If this store only had one suit in stock, just one single item hanging on a lonely rack, and you tried it on and it fit you perfectly. The sleeves were the right length, the waist was perfect, the shoulders were exact, you would be shocked. You would think, this suit must have been made for me. It would be too perfect to be a coincidence. But if the store is truly infinite, filled with millions and millions of suits in every crazy shape and size, the situation changes. In this giant store, there are suits with 3 arms. There are suits made for giants and suits made for ants. There are suits made of lead and suits made of gas. There are billions of suits that would never, ever fit you. But because the inventory is infinite, somewhere in those endless racks, there must be a suit that fits you perfectly. Finding it isn't magic, it's just statistics. If there are enough suits, one of them is bound to be the right size. Rees believes that universes are like those suits. In the vastness of the cosmos, there might be an infinite number of universes, and each one is different. Each one has its own settings. In one universe, maybe gravity is turned way up high. That universe is a bad suit. It collapses instantly into a black hole, and no life can ever form. In another universe, maybe the nuclear forces are too weak. That universe is a loose suit. It just floats apart into a thin, cold mist, and stars never ignite. There could be trillions and trillions of these failed universes. Universes that are dark, dead, too hot, too cold, or just plain weird. They are out there, popping into existence and fading away, unseen and unknown. And then there is our universe. We are the suit that fits. We happen to be living in the one bubble where the numbers lined up. In our bubble, gravity was just right. In our bubble, hydrogen turned into helium at exactly 0.007%. In our bubble, the stars turned on and stayed on. The reason we see this perfection around us isn't because the universe was designed for us, but because this is the only kind of universe we could exist in. We are here because we are here. If the universe were different, we wouldn't be here to notice it. We are like the customer in the clothing store who found the perfect fit. We don't see the millions of discarded outfits on the floor, we only see the one we are wearing. This idea changes how we feel about our place in the dark. It makes us feel a little less special, perhaps, because it means we aren't the chosen ones, but just the lucky winners of a cosmic game of chance. But it also makes the universe feel much, much bigger. It paints a picture of a meta-universe, a grand landscape where universes are blooming like flowers in a field, each one different, each one an experiment in physics. Some scientists, like Edward P. Tryon from Columbia University, have a very relaxed way of looking at this. He once offered a modest proposal. He said, simply, our universe is simply one of those things which happen from time to time. I love that sentence. It takes the most massive, explosive, complex event in history, the creation of everything, and treats it like a common occurrence. It suggests that creating a universe isn't hard. It's just something that nature does, like a cloud making rain or a tree making leaves. Although creating a universe like ours, one that supports life, might be very rare and unlikely, Tryon and Guth remind us that no one had counted the failed attempts. We don't see the failures. We don't see the billions of universes that collapsed or froze. We only see the success. So, as you lie in bed, imagine that you are floating not just in space, but in a sea of bubbles. Some of those bubbles are popping, some are shrinking, some are flying apart too fast. But you are safe inside a Goldilocks bubble, a rare and precious sphere of stability, where the laws of nature have aligned to let you breathe, sleep, and dream. We are the survivors of the great cosmic lottery. We are the ones who found the suit that fits. And whether that is by grand design or just by infinite chance, the result is the same. We are here, and it is beautiful. So, we have found our place in the multiverse. We are wearing the suit that fits. We are living in the lucky bubble where the laws of physics allow us to exist. It feels very comfortable, doesn't it? Knowing that we are in the Goldilocks universe, where everything is just right. But, as with all good stories, there is a twist. Just because things are perfect right now doesn't mean they will stay that way forever. We have talked about the birth of the universe, and we have talked about its childhood, but now we have to talk about its future. We have to ask the ultimate question: how does the story end? Let's talk about the universe's fate. To understand this, we have to look at a giant cosmic arm wrestling match that is happening all around us every single second of every single day. It is a battle between two titans. On one side, we have the energy of the Big Bang, the momentum of that initial explosion that is still pushing the galaxies apart, stretching the universe outward, trying to make it bigger and bigger. On the other side, we have gravity. Gravity is the puller. It wants to grab everything and bring it back together. It wants to hug the universe tight. Right now, the expansion is winning. The universe is getting bigger. But the question is, will it win forever? Or will gravity eventually overpower it? The answer depends entirely on how much stuff, how much matter and density is actually out there in the dark. Scientists have outlined three main possibilities for how our universe will end. They are like three different endings to a choose-your-own-adventure book, and they depend entirely on the strength of that gravity. The first ending is what we might call the Big Crunch. Imagine that in the long term, gravity turns out to be a little bit too strong. It is patient. It waits. For billions of years, the universe keeps expanding, but slowly, imperceptibly. Gravity acts like a brake on a car. It starts to slow the expansion down. Eventually, billions of years from now, the car stops completely. The expansion halts. The universe reaches its maximum size, hangs there for a moment in silence, and then it starts to reverse. Gravity takes control. The galaxies stop rushing away from each other and start rushing toward each other. The universe begins to shrink. It collapses in upon itself. It gets smaller and hotter and denser. It is like watching a movie of a breaking vase played backward. All the shards fly back together to form the whole. In this version of the end, everything we know, every star, every planet, every atom, gets crushed back down into a single point. We return to the singularity. We go back to being that tiny, dimensionless dot we talked about at the very beginning. Some people find this idea scary, but others find it poetic. There is a theory that suggests this might be a cycle. Perhaps the universe is like a giant lung, breathing in and breathing out. Maybe the Big Bang happens, the universe expands, breathes in, then it stops and collapses, breathes out, and then once it is crunched back down to a dot, it triggers a new Big Bang. This idea suggests that maybe we are just one in an eternal chain of universes, expanding and collapsing forever, like the bladder on an oxygen machine, pulsing in the dark eternity. But that is only if gravity is strong. What if it is weak? This leads us to the second ending, which is often called the Big Freeze or the open universe. In this scenario, gravity is too weak to stop the expansion. The force of the Big Bang was just too powerful. The universe is like a rocket that has escaped the pull of the Earth. It isn't coming back. It just keeps racing away forever. The galaxies get further and further apart. The space between things stretches out until it is vast and uncrossable. In this future, the universe doesn't end with a bang or a crunch. It ends with a whimper. It becomes a place that is inert and dead, but very, very roomy. Over trillions of years, the stars will burn up all their fuel and fade away. New stars won't be able to form because the dust is too spread out. The lights will go out, one by one, until the cosmos is just a vast, cold, dark ocean of nothingness, expanding forever into silence. It is a lonely ending, a fading away into the night. So, we have the Big Crunch, too hot, too crowded, and the Big Freeze, too cold, too lonely. But remember, we live in the Goldilocks universe. We live in the place where things seem to be just right. This leads us to the third option, the one that many cosmologists believe is the most likely. It is called the flat universe. In this version, the strength of gravity is perfectly balanced with the energy of the expansion. It is a concept called critical density.
Imagine rolling a ball up a hill.
If you roll it too hard, it goes over the top and rolls away forever. Open universe. If you roll it too softly, it stops halfway up and rolls back down to you. Closed universe. But if you roll it with the exact perfect amount of energy, it will roll up the hill and come to a gentle stop right at the peak, and just stay there. In a flat universe, the expansion slows down, but it never quite stops, and it never reverses. It just continues on a steady, balanced path. It holds the universe together at just the right dimensions to allow things to go on indefinitely. It avoids the fiery crunch, and it avoids the runaway isolation. It is the perfect middle ground. So, which one is it? Are we going to crunch, freeze, or stay balanced? Well, measuring this is notoriously difficult. We are trying to weigh the entire universe from the inside, which is like trying to guess how much your car weighs while you are sitting in the driver's seat. But the consensus right now seems to be that we are very close to that critical density. We seem to be in the flat universe. We are balancing on that knife edge of perfection. However, science is always surprising us. Just when we think we know the answer, we find something new. For a long time, we thought gravity was the only player in the game. But recently, we have started to wonder if there are other forces at work, things we don't understand yet that might be pushing the universe apart even faster. But based on the simple mechanics of gravity and mass that we discussed in our original paragraph, the choice remains between these three fates: the closed circle, the open road, or the flat balance. For tonight, though, you don't need to worry about the sky falling or the stars rushing away. These are events that play out over timescales so huge that a human life is less than a blink of an eye. For us, for now, the universe is stable. It is holding us. It is expansive enough to give us room to dream, but cohesive enough to keep our sun burning and our feet on the ground. We are safe in the just right zone, floating in a cosmos that has managed to survive its violent birth and navigate the chaos of its youth to arrive at this quiet, beautiful moment of now. So, whether the future holds a crunch, a freeze, or a long, steady ride into eternity, we can rest easy knowing that for the next few billion years, at least, the show will go on. The stars will rise, the planets will spin, and we can sleep soundly in our little corner of the vast, mysterious, and perfectly balanced dark. So, we have journeyed from the very first spark of the Big Bang, through the wild expansion of inflation, past the accidental discovery of the background noise, and all the way to the possible ends of time. We have talked about when things happened and why things happened. But there is one final, mind-bending piece of the puzzle we need to place before we can rest. We need to talk about where we actually are. We need to talk about the shape of this giant house we live in. Now, I know what you are thinking. You are picturing the universe as a giant ball or a giant bubble floating in nothingness. And naturally, a question pops into your head, a question that every single person has asked at least once since they were a child. What would happen if I traveled all the way to the edge of the universe? It is a fun thought experiment. You imagine getting in a super-fast spaceship, flying past Mars, past Pluto, past the nearest stars, and just keeping going in a straight line. You fly for billions and billions of years until finally you reach the end. You imagine a wall, or maybe a velvet curtain hanging in space. And you imagine parking your ship, opening the hatch, and poking your head through that curtain. What would you see? Would you see the back of the set? Would you see a sign that says, "The End"? Would you see just pure white nothingness? The answer, I am afraid, is a little disappointing, but also fascinating. The answer is that you can never get to the edge of the universe. And no, it's not just because it would take too long. Even if you were immortal, and even if your ship could fly forever, you would never find a boundary. You would never hit a wall. Instead, if you traveled outward and outward in a perfectly straight line, indefinitely and stubbornly, something very strange would happen. You would eventually find yourself back exactly where you started. You would fly past the back of your own head. This is because the universe isn't a simple bubble. It bends. According to Albert Einstein and his famous theories, space itself is curved. It curves in a way that our human brains, which are used to simple things like tables and floors, can't quite imagine properly. To help us understand this, scientists use a wonderful analogy. Imagine a little 2D person, let's call him Flatlander, who lives on a perfectly flat world. He has never seen a sphere or a ball. Now, imagine you take this Flatlander and put him on the surface of the Earth. To him, the ground looks flat. He starts walking in a straight line, looking for the edge of the world. He walks across oceans and continents. No matter how far he roams, he never finds an edge. He never falls off. Eventually, if he keeps walking, he will come right back to the spot where he started. He would be totally confused. He would say, "I walked in a straight line. How did I get back here?" Well, we are in the same position as that puzzled flatlander. The only difference is that we are flummoxed by a higher dimension. Just as the Earth is a sphere that has no edge on its surface, the universe is a shape that has no edge in space. It is boundless, but finite. It curves back on itself. This also solves another riddle. Where is the center of the universe? When we think of the Big Bang, we think of an explosion. So we assume there must be a center point where the explosion happened, like the crater of a volcano. We want to be able to point a finger and say, that is where it all began. But just as there is no edge, there is no center. Or, to be more accurate, everywhere is the center. Think of our flatlander on the Earth again. Ask him to point to the center of the surface of the Earth. Is it London? Is it New York? 1994. Is it the North Pole? No. No. Every point on the surface is equal. There is no center on the surface of a ball. In the same way, every point in our universe is expanding away from every other point. We are all at the center of it all. It is a challenge to our intuition, but as the biologist J.B.S. Haldane once famously said, "The universe is not only queerer than we suppose, it is queerer than we can suppose." So we live in a curved, edgeless loop. But how big is it? Well, we can only see as far as light has traveled in the 13.7 billion years since the birth of everything. This is called the visible universe. It is a bubble roughly 1,000,000,000,000,000,000 miles across. That is a number so big it makes your head hurt just trying to think of it. But most theories suggest that this visible bubble is just a tiny speck compared to the real universe, the meta-universe. The real universe is likely vastly roomier still. According to Martin Rees, the distance to the edge of the unseen universe wouldn't be written with 10 zeros or 100 zeros, but with millions of zeros. In short, there is more space than you can possibly imagine, so you don't need to worry about feeling cramped. Now, before we end our quest, we have to look at one last problem. We have built a universe, we have shaped it, and we have expanded it. But what is it made of? For a long time, the Big Bang Theory had a gaping hole that troubled a lot of people. The theory explained how we got the expansion, and the heat, and the radiation. But it couldn't explain how we got us. You see, the Big Bang was a nuclear oven, but it was a very simple oven. In those first 3 furious minutes we talked about earlier, the Big Bang created 98% of all the matter that exists. But that matter consisted exclusively of light gases, hydrogen, helium, and a tiny dash of lithium. That was it. The problem is, you and I are not made of hydrogen and helium. We are made of the heavy stuff. We are made of carbon, nitrogen, oxygen, iron, and calcium. These are the elements vital to our being. Without them, there are no bones, no blood, no leaves, no rocks. But, and here is the troubling point, to forge these heavy elements, to mash atoms together, to make carbon or iron, you need incredible heat and pressure. You need the kind of energy you find in a Big Bang. Yet, there has been only one Big Bang, and it was too busy making gas to make the heavy stuff. So where did the carbon in your genes come from? Where did the oxygen in your lungs come from? The universe started with a simple gaseous brew, lighter than air. Not one particle of the heavy stuff existed. So, for a long time, it was a mystery. Side, how did a universe of gas turn into a universe of people? The answer to that question is one of the most beautiful discoveries in science. And ironically, it was found by a man who hated the Big Bang theory. But that is a story for another night. For now, it is enough to know that we are standing on a stage that is curved, limitless, and ancient. We are floating in a vastness that loops back on itself, filled with mysteries that we are only just beginning to solve. We have traveled from the singularity to the edge of our understanding. We have seen how a tiny dot became a cosmos, how silence became a symphony of forces, and how the nothing became the everything. It has been a long journey, but now it is time to rest. The universe has been doing its work for billions of years, and it will continue to do so while you sleep. The stars will hold their places, gravity will hold you safe, and the great curved, expanding dark will watch over you. Good night, fellow travelers. Sleep well in this wondrous, impossible place we call home.